In this section, we discuss how to visualize the performance of AutoML systems. We have established that AutoML systems are anytime algorithms, that their evaluation requires nested protocols, and that differences between systems must be assessed with statistical tests. Visualization is the bridge between these formal tools and human understanding. This is how we communicate search dynamics, compare systems, and build intuition about what is actually happening during the optimization. As we will see, doing it correctly is less straightforward than it might appear. Let us start with the motivation. Recall that an AutoML system maintains an incumbent, the best configuration found so far, and updates it whenever a strictly better configuration is discovered. The system can be stopped at any point in time and return this incumbent. This anytime property is one of the defining characteristics of AutoML systems, and it has a direct consequence for how we should report and compare them. The most natural summary of a system's performance is a single final value, the risk of the incumbent after the full search budget T has been depleted. This is simple to compute and easy to report in a table, but it discards almost everything interesting about the system's behavior. Consider what a single final value cannot tell you. It does not tell you how quickly the system found a good solution. A system that reaches near optimal performance in the first 10% of the budget and then stagnates looks identical to one that improves steadily throughout. It conflates systems with very different search dynamics under the same number. And it is sensitive to the choice of the budget T. Rankings between systems can and do change as the budget varies. A system that appears better at t equals 1 hour may be worse at t equals 10 minutes or t equals 4 hours. The motivating question for this section is therefore, given two AutoML systems, A and B, can we say which is better and under what conditions? Answering this question requires understanding the full trajectory of the incumbent over time, not just its final value. The natural visualization is the anytime performance curve, also called the incumbent trace. It plots the incumbent risk as a function of time t or the number of function evaluations. At each point in time, the curve answers a specific question. What is the best solution the system could return if stopped right now? From such curves, we can draw three qualitatively different kinds of conclusions, and it is worth distinguishing them carefully. The first and strongest is anytime superiority. System A dominates System B if its incumbent curve is uniformly better across all time points. That is, at every moment throughout the search, A has found a better solution than B. This is a budget-independent conclusion. Regardless of when you stop the search, A is preferable. This is the strongest possible statement we can make about two systems. The second is crossover behavior. It is entirely possible that A converges faster early in the search, while B overtakes A given sufficient time. This kind of behavior is completely invisible in a single final value. The relative ranking depends entirely on when you look. Only the full curve reveals it. The third is budget sensitivity. Comparing systems at a specific fixed time point t. This is a weaker statement. It is valid for the specific deployment scenario where budget t is fixed, but it cannot be generalized beyond that budget. The practical implication is this. A single final value is only sufficient when the budget is fixed in advance and anytime behavior is genuinely irrelevant. For any general comparison of AutoML systems, the full curve is necessary. Before we discuss how to aggregate curves across multiple runs, we need to establish a fundamental property of individual curves. They are step functions. The incumbent is defined as the best configuration found up to time t. Its risk is the minimum over all configurations evaluated so far. This quantity only changes when a strictly better configuration is found. At that moment, the curve steps down to the new incumbent's risk. Between two improvement events, the incumbent and its risk stay constant. There's no gradual improvement between evaluations. Performance is flat and then it steps down. This has a direct implication for plotting. Connecting the points where improvements occur with straight lines implies that performance improved gradually between those events, as if the system was continuously getting better in between. This is not what happened. The system found nothing better during that interval. The incumbent was unchanged. Linear interpolation misrepresents the search dynamics and can make a slow converging system appear faster and smoother than it actually is. The correct representation is a right continuous step function. The curve stays flat at the current incumbent's risk until an improvement was found or occurs, at which point it then drops instantaneously to the new value. This is a simple setting, but it matters, and it is frequently violated in published plots. Always use step functions. A single run of an AutoML system is a single draw from a stochastic process. The specific configurations proposed, the order in which they are evaluated, and the performance estimates assigned to them all depend on the random seed. A conclusion drawn from a single run is no more reliable than a conclusion drawn from a single train test split, which we established in the evaluation section is insufficient. We therefore run the system n times with different random seeds, obtaining n step functions. To aggregate these into a single representative curve, we proceed as follows. First, we define a common time grid, a set of time points at which we will evaluate all runs. At each time point tj, we read off the incumbent value for each run I, because each fi is a step function. This is well defined. The value at tj is simply the best configuration found by run I up to that moment. We then compute the pointwise mean as the average of these n values. There's a subtle point worth noting explicitly. The mean curve is a summary statistic across runs. It is not a valid incumbent trace of any single run. In particular, it may appear smoother than any individual run, because averaging tends to smooth out the discrete time steps. Sometimes the mean curve is interpreted as a typical trajectory of the system, which it is not. It is the expected incumbent performance at each time point averaged over the randomness of the search. So, once we have the mean curve, we need to add uncertainty bands. The first and most intuitive choice is the standard deviation. At each time point tj, we compute the standard deviation of the n run values around the mean. Shading the region between the mean values minus plus the standard deviation gives a band that characterizes the spread of the individual runs. A wide band at a given time point means that runs differ substantially from one another at that moment. Some found a good solution quickly, others did not. A narrow band means the runs are consistent with each other. This is useful information when we want to understand the stability of a system, for instance whether one system is more sensitive to the random seed than another. However, the standard deviation is the wrong quantity when our goal is to assess the reliability of the mean curve itself, or to compare two systems. The reason is that the standard deviation characterizes the variability of the individual runs, not the precision of the mean. As n grows, the standard deviation converges to the true run-to-run variability of the system. It does not shrink to zero. Even with 100 runs, the standard deviation band remains wide if the system is inherently variable. This means that two systems with very similar mean curves but high run-to-run variance will have widely overlapping standard deviation bands, even if we have estimated their means very precisely. Standard deviation bands are therefore not informative for comparing means. Instead, the correct quantity for assessing the precision of the mean curve is the standard error of the mean, which we obtain by dividing the standard deviation by the square root of n of the number of runs. It measures how precisely we have estimated the pointwise mean from the n available runs. Unlike the standard deviation, the standard error shrinks as n grows. With more runs, our estimate of the mean becomes more precise, and the SE band narrows to reflect this. Shading the region in between the mean minus plus the standard error gives an approximate 68% confidence band for the true mean curve. If you want a 95% confidence band, use 1.96 times the standard error instead. These are then the standard normal approximations, which are reasonable for moderate n. The practical recommendation is therefore use standard error bands when the goal is to compare methods or communicate the reliability of the mean curve. If run-to-run stability is also of interest, for instance if you want to show that one system is more consistent than another, You can report standard deviation separately, for example in a supplementary figure or as an additional shaded region with a different transparency. With mean curves and standard error bands in hand, we can now think about how to compare systems visually and what conclusions we are licensed to draw. The most direct visual comparison is to plot each system's mean step function with its standard error band on the same axis. What can we conclude from what we see? If the standard error bands of two systems do not overlap at a given time point, this is indicative of a statistically meaningful difference at that budget. It is not a formal test. Overlapping or non-overlapping bands are a visual heuristic, not a p-value. But non-overlapping bands provide reasonable informal evidence that the systems differ. For a formal comparison at a specific time point, we extract the n-run values of each system at that time and apply the Wilcoxon signed rank test, exactly as discussed in the statistical test section. If the bands overlap, we cannot conclude equivalence. As with the hypothesis testing, absence of visual separation is not evidence of equality. The systems may differ, but our estimate of the mean may not be precise enough to see it clearly. Crossovers deserve special attention. If the mean curve of two systems cross at some time, t star, neither the system dominates the other. The conclusions depend entirely on the deployment budget. One system is preferable before t star, the other after. In this situation, reporting a single final value at an arbitrarily chosen t is particularly misleading because the choice of t determines the conclusion. Uniform dominance, on the other hand, is the cleanest possible result. One system's mean curve is consistently below the other across the entire time axis. If this pattern is supported by non-overlapping standard error bands or formal tests at multiple time points, the conclusion is generally budget independent. On the practical side, use distinguishable colors and line styles so that plots remain readable in grayscale and for readers with color vision deficiencies. Always label both axes clearly, the performance metric, the time unit, and whether the scale is linear or logarithmic. A log scale on the time axis is often more informative for anytime plots because early improvements tend to be rapid and later improvements more gradual. So a linear scale compresses this information too much and the log scale makes this more visible. Let us close this video with the key takeaways. A single final performance value discards most of the information about an AutoML system. The full anytime curve is necessary for budget-independent comparisons and for detecting crossover behavior between systems. Anytime superiority, one system's curve is uniformly below another's, is the strongest conclusion we can draw. Crossovers and budget-specific comparisons are weaker. Anytime performance curves are right continuous step functions. Linear interpolations between incumbents misrepresents the search dynamics and must be avoided. Always use a step function renderer. Multiple runs are required. Aggregate by computing the pointwise mean on a common time grid and keep in mind that the mean curve is a summary statistic across runs, not a valid single run trajectory. Use standard error bands rather than standard deviation bands when comparing methods because standard error measures the precision of the estimated mean rather than the spread of individual runs. Non-overlapping standard error bands are indicative of a meaningful difference, but for a formal conclusion, apply statistical tests at the time points of interest.